Okay. So last time we were talking, well, I talked about 3D printing, and the generalization of the story about 3D printing is don't believe all the hyperbole you hear in the press about some sort of new material or new process. The guy, Bob Sprague, I quoted him before. He was head of materials for GE aircraft engines for 20 or 30 years. And the quote I like from him is, whenever you first hear about the properties of a new material, write it down, because those are the best properties the material will ever have. Yeah?
I was wondering, is there any issue with directionality with 3D printing of metals like there is with plastic? The orientation of the part matters a great deal.
Only in terms of gravity, okay? I mean, but there's no structure like the wood structure, you know, an anisotropic, if that's what you're talking about, because it's basically a bunch of little castings. And you don't get, because of the low thermal conductivity, or the high thermal conductivity, it really just, it's a little sphere that, you can think of it as a little sphere that solidifies. You don't get a lot of columnar growth and things like that. In fact, that Inconel 100 piece, that little flat piece I sent around, you actually get very fine grain size because you're doing rapid cooling, and you'll have very small flaws or inclusions and other things because of the rapid solidification time. It's not super rapid. It's not 1,000,000 degrees per second, but it is on the order of probably between 1,000 and 10,000 degrees per second. It's cooling very quickly, and that gives you relatively small defects, because the defects are generally proportionate to the size of the casting. Well, this casting's pretty small. It's only a couple of millimeters in size or smaller. And so you get very fine structure, which gives you very good properties. It's fairly uniform. It's fairly isotropic. I guess that's your question, right? So it's isotropic in general. In fact, it'd be hard to make it anisotropic because of the very fine grain size that you get. Okay, and that's because of the high thermal conductivity and rapid cooling time. So anyway, Bob Sprague said, whenever you first hear about the properties of a new material, write it down. Those are the best properties the material will ever have. And the person who replaced him, Jim Williams, who had been dean at Carnegie Mellon and now then left after being at General Electric for about 10 years, became dean at Ohio State. Jim Williams had a corollary to that, which is whenever you first hear about the price of a new material, write it down. That's the lowest price the material will ever have. Okay? People always glorify their material and tell you wonderful things about it. You have to be very careful about what people tell you about a new material. About 30 years ago, I was sitting in what was the Chipman room back then, listening to a talk from a new young professor who was working on electrically conductive polymers. Okay, anybody familiar with electrically conductive polymers? The first one that came out was polyacetylene. And these are polymers with lots of double bonds. And so they have some free electrons, which means they can be electrically conductive. The only problem is they tend to decompose in air, okay, the humidity in the air and stuff. But they're very light, and he was talking about, he mentioned something that I never thought about before. He said that these were going to be the material of the future. They were going to replace copper because the specific electrical conductivity of polyacetylene and these new electrically conductive polymers was less than that of copper. Okay, and copper is our electrical conductor we use in general. And that sounded pretty impressive to me. I mean, copper had already taken a big hit from the fiber optics community, where you now have, you know, photons carrying the information for data and stuff. And now we're basically going to have plastic wires that carry electricity because they have a lower specific electrical conductivity. What does it mean to have a specific electrical conductivity or a specific thermal conductivity or whatever? What does the word specific mean? Per unit mass. You divide by the density. Or you, let's see. Yeah, per unit mass. You divide by the density. So, and that sounded pretty impressive, except the next morning when I was shaving, I almost cut myself when I realized, well, wait a second, aluminum has a lower specific electrical conductivity than copper today. And we've been using mostly copper rather than aluminum in rotating machinery and things like that, because the important parameter for selection of material in something like a big motor or a generator rotor is not specific electrical conductivity. It might be rotating and you might want lightweight, except you really want the best conductivity. You don't want the best specific conductivity divided by density in that case. You want the best electrical conductivity. And the only thing with better electrical conductivity than copper is silver. Well, there's an obvious reason we don't use silver for big motors and stuff. Although during World War II, when they were separating uranium in the magnetic separators at Oak Ridge, and basically it was a great big mass spec, they were separating uranium-233 from 238 or whatever, or vice versa, I can't remember. They had a shortage of copper. All the copper was being used for shell casings, for the guns. And so it turns out they borrowed something like 50 tons of silver from the U.S. Mint in Philadelphia, and they wound their magnets out of silver at Oak Ridge, okay, to make the nuclear weapon. And after the war, they had to return the 50 tons to the U.S. Mint because it didn't deteriorate in service. But silver is the only one that would be better to wind the electrical windings of great big motor forgings, unless you have a superconductor that works, okay? But that's another story. I could spend an hour on that story about high-temperature superconductors and whether they're going to make big magnets and things. In any case, you have to be careful when people are telling you about the properties of new materials because they often oversell them, to be frank, okay? Hey, it's their product, their marketing. And remember, it's like the person who calls you on the phone and wants to sell you something. Okay, it's the same thing. Okay, they're usually not telling you the whole story. And so it helps to get the whole story. Then we talked about externalities. We started talking about externalities. And I guess what I want you to know is increasingly, well, actually, when I taught this course a few years ago, I used to say the most important parameters were price and availability of a material. Okay, the cost of the material and whether it was available. Well, it turns out more and more those are being taken a back seat to the externalities. Does anyone remember the definition of externality? An externality in economics is something where someone else has to bear the price of something that they had not intended to bear the price of. And that could be air pollution, water pollution. It could be all kinds of, it can be political, economic, social, environmental, military. Lots of different things are now influencing things more than just the basic properties of materials. So we talked about rare earth metals and how China basically decided to hold Japan hostage and actually, and by extension, the rest of the world in electronics by withholding the rare earth metals. Not because they had a monopoly on the availability of the rare earth metal ores, but because they had been willing to accept the pollution, been willing to pay their workers very low wages, because that's the going rate in China, and they had basically gotten a de facto monopoly that has a hurdle of probably 5 years before someone else could enter the market. Okay, so you can't just stop all the production of electronics in Japan for 5 years. You're going to have to pay the price somewhere else. So same type of thing as the oil embargo of '73. We talked about economic sanctions that have to do with environmental things. We started to talk about social things where people want to get the lead out of things and people will pay a fortune. I was actually the person who helped get rid of Building 20. You don't know Building 20, you know the Status Center. But in World War II, to develop radar, they built Building 20, which was on the site of what is now the Status Center. And it turns out the building was nothing but asbestos. but it was considered a wonderful incubator because it was wood framed and you could tear down walls and all kinds of great things. Some people wanted to turn it into a National Historic Landmark for all the great innovative science that had been done in Building 20. I looked at it and said, that's a big asbestos liability, and someday it'll cost us a fortune to bulldoze that and get rid of it. We'll have to clear out Cambridge and wrap it in a big plastic bubble because someone's afraid we're going to release some asbestos. And so it turns out when they built the new biology building 20 years ago, 25 years ago, almost 25, yeah, 25 years ago now, the physicists were supposed to backfill into building 16 and 56, which is where the biology department had been, and they came in and said, oh, that space is no good. That's not good enough for us. We're the physicists. And we want a new building. And they wanted to build a building right there. And that's the building they wanted to build. But this is 1992, and peace had broken out. And MIT was looking at decreasing research budgets because we weren't going to get all this money from the Defense Department. And so they came to Extended Engineering Council, and they discussed how the physics department wanted to build a new building and charge all the rest of us $50 million on our overhead base so they could have a nice new building, because 16 and 56 were not good enough for the physicists. And I raised my hand and said, well, tell the physicists to stay where they are. We're not going to have a bigger research budget. We can't afford this increased overhead. And what's more, why don't you take the people in building 20 and move them into 16 and 56 if you have empty space, and you can tear down building 20. And they said, well, what will the physics department do for a new building? And I said, give them a hunting license. Let them, whichever school, the School of Science or the School of Engineering, can come up with the money to build on that site first, they get to build a new building. And people said, well, what if the physics department comes up with the money before the School of Engineering? I said, they've been trying for 30 years, and all they raised was $3 million for a new building. I said, who in this room, which is Engineering Council, thinks the School of Engineering couldn't raise the money for a new computer science, electrical engineering building faster than the physics department has done in the last 30 years? And everybody said, oh, yeah, that's right. So it turns out that's what they told the president of MIT. Give the School of Engineering and School of Science, put them in competition to raise the money for a new building. And so Joel Moses went out, and within a year and a half, he had $115 million committed to build the Stata Center, okay? And then they spent $430 million on it, so it didn't quite work out financially the way we wanted because they didn't stick to the agreement, but that's another story. Anyway, the point is asbestos and things like that become unacceptable over time socially. Environmental carbon-free metal reduction. It turns out if you look at the free energy diagrams, actually, which I happen to have here, every metal on the periodic table can be reduced from its oxide using carbon if you go to a high enough temperature. So this is a book on thermodynamics, which we used to use. It's in the 5th or 6th edition here. But this is an Ellingham diagram. And this is the free energy of formation versus temperature. And you see that the free energy of formation increases for every metal on the periodic table. I guess I can blow it up even bigger. This is a fairly complex diagram. I used to kind of base the final exams on this diagram. But in any case, you'll see that the free energy of formation increases for cobalt and iron, and you can see which ones are more stable. Down here you got aluminum and calcium and stuff. But you notice the carbon plus oxygen going to carbon monoxide has a negative slope. Okay? That means that carbon monoxide, if you go to a high enough temperature, will eventually become lower than the free energy of formation of any of the other oxides on the periodic table. And therefore, if you go to high enough temperatures, any metal can be reduced from its oxide ore to the metallic form using carbon. Well, it turns out today we're trying to get rid of the CO2, as Professor Sadoway used to say. If making metals in billion-ton quantities is the problem of generating a lot of CO2, maybe it's not as bad as the cows generating methane or the utilities generating electricity. But the metals business produces a lot of CO2 because we make things in very large quantities. And so Professor Sadoway said, well, then we should be the ones to figure out how to clean it up and get away from carbon-free metal reduction. And so Professor Alanor, Professor Sadoway, and a number of other people in the department have various schemes to generate metals without using carbon. Now, in general, they're going to do that by using electrons. And today, where do most electrons come from? The utility, which burns coal, is in the news this morning. However, you do have hydroelectric plants, you have nuclear power. You could maybe think of solar, but you'd have to have a very large solar grid to get to the thousands of megawatts of power you need. Nonetheless, nuclear and hydroelectric, and in fact, aluminum plants are located at the source of the electricity. Great big hydroelectric power plants in Norway or James Bay in Canada, or originally it was Niagara Falls. Where did Charles Martin Hall built and Alcoa built their first reduction plant? Niagara Falls, because it was a source of free electrons, relatively free electrons. Okay, the military. Anybody know the story of Japan and oil and steel? It's called World War II. You may not have heard about it before, but we always say the Japanese did a sneak attack on Pearl Harbor. Why? Let's ask the 5 whys. Why did the Japanese go to war with the United States? Well, they did it because we had decided to withhold from them all the scrap iron and steel and raise the prices and stuff on scrap iron and steel. And so we were stopping their steel economy in Japan. And so they were trying to be a military power, and they already controlled Korea, and they wanted to go into China, and they had imperialistic inclinations. We also, at that time, were probably the major exporter of oil in the world. Okay, and so we were essentially doing to them, the Japanese, what the world does to North Korea today. We put them in isolation. Okay, what we do to Iran today to get them to stop their nuclear thing. Well, the Japanese basically decided they would try to do a sneak attack on Pearl Harbor because we were playing games with the oil and steel business. Okay, cultural gold. Where's half the gold? Well, there's one country that contains half the world's gold. Anybody know what it is? No. India. Who said that? Yeah. How do you know it's India? You're right.
Just culturally, because I've had friends and I've also seen in shows that they wear a lot of gold.
Exactly. It turns out Indian people from India have slightly darker skins, and it matches very well with gold. And if you go anywhere in India, you'll see people, some of the poorest people in India will be wearing gold jewelry. And there are 1 billion of them. And it turns out that half of all the world's gold reserves that have ever been mined are mostly on the necks and wrists of people in India. Okay? We may have more in our central bank than anyone else in Fort Knox, but India has more on people's necks and arms. Okay? It's a cultural thing. Okay, now, and platinum jewelry is very popular in Asia because people like the color of platinum with the color of the skin. I mean, so there are cultural things about jewelry production. Regulatory, utilities, and the rate base. Anybody know what a rate base is for a utility? A utility is a regulated monopoly, okay? We don't have 2 companies that deliver electricity to your home. We have one. And in the old days, we had something called American Telephone and Telegraph. We actually still do. But it was a regulated monopoly in the old days. And in a regulated monopoly, the regulators in the government will actually set the profitability of the company. It turns out people used to think, wasn't it foresightful for AT&T to run Bell Laboratories and spend all this money on basic research? Well, that's a load of bull, okay? AT&T had a promise from the regulators that they could make 6% profit on whatever they could justify spending. And they could justify spending on a huge research facility, okay? And that wasn't, they did a lot of great basic research, okay? But almost all of it was aimed at improving the productivity of and the reliability of the telephone system. You'll hear that, oh, they invented the transistor, and that came out of basic research. Another fallacy, okay? The transistor was developed because in 1925, AT&T had statisticians who were looking at the reliability of the phone system. At the time, it was little mechanical switches. You know, you see the old TVs and the person taking the telephone operator taking the plug and putting it from one hole to another. And they were switching like that. But when they were putting the plug in, it was a mechanical plug. And anyone who looks at mechanical things, they know that after 10,000 hours of operation or whatever, they tend to fatigue or wear or whatever, and they break. So from 1925 on, it turns out Bell Laboratories was trying to find a replacement for the mechanical switch because they could plot the increased use of phone usage, and they knew that sometime in the 1950s, the entire system would break down because to make a phone call from A to B, you would have to go through so many switches that the probability of failure would be horrendous, and the system would just collapse because it would be unreliable. The transistor came out of a study, an applied study, to find an electrical switch that would be more reliable than a mechanical switch. But how many of you have heard that the transistor is evidence of how basic research, pays off? Well, except it's not basic research. It was applied research. And it was a regulated industry. They could make 6% for every dollar that they could spend. They just had to justify that what they were spending it on had some basis in improving the phone system. Well, that's still true in the utilities business in terms of the electrical utilities, the water utilities, all these other people. Basically, they have commissions usually run by the state. In Massachusetts, it's the Department of Public Utilities, and they basically set the profitability of these companies, and say they'll look at them critically, and they'll say, "We'll let you make 5%, so that people who invest in your stocks can put them in their pension fund and make enough money to retire." And whatever you can afford to spend, you can spend. Anyone gone to the store and bought some LED light bulbs that were discounted because the local utility was paying $7 for that light bulb? Why do they do that? Do you know?
I think they want you to switch over so they can have better peaking, and is that true?
Yep, that's true. That's part of it. But it's really an economic reason. It turns out to build a new power plant, to build a new power plant, they typically come in at, a big one comes in at 1,000 megawatt electric power generation, okay? 1,000 megawatts is 1 billion watts, right? Well, it turns out the installed price to build that plant is about $2,000 a kilowatt, okay? Well, if you could save electricity at less than $2,000 a kilowatt, it's more efficient for society to give you efficient light bulbs. If they can give away light, reduce the price, give you a discount on the cost of a light bulb for less than $2,000 a kilowatt over the life of that light bulb, it's a win-win. And so the regulators basically say, we'll let you make a little more on all these discounts you'll give on energy efficient equipment and light bulbs and things like that. So you won't have to tear out half of Belmont to build a generating station, okay? Having lived in Belmont, be okay if they actually, no. No one wants the coal-fired plant in their backyard. Not even a gas-fired plant. Not even they don't even want hydroelectric plants. They really don't want any electric plant in their backyard. Take the people in Martha's Vineyard in Nantucket. They don't want those windmills destroying their view of the ocean. Okay? Now wait a second. If you told them, we're going to triple your electric bill because that's what you want, would they say yes or would they say no? But that's not what people tell them. They say, oh, it's going to destroy my view. Okay, but what is the choice? The choice is, and we're now paying over 20 cents a kilowatt hour in Massachusetts. Okay? Anyway. But those are externalities on what we choose to do. Embargoes, there were blood diamonds in Angola back longer ago than actually when your parents were in diapers. Rhodesia, which is now part of Zimbabwe or some way. Anyway, there was Rhodesia, which is just northeast of South Africa. They had the world's best chromium reserves. They had a civil war going on. And the world tried to put pressure on them, just like we try to put pressure on North Korea and Iran and other countries to not build nuclear weapons and stuff. Rhodesia wasn't building nuclear weapons, but it was a lot of pain and suffering for a lot of people there. And so we basically said, we're going to put an embargo on Rhodesian chrome. They had the best chrome ore in the world. It was so good, you could basically just take that rock and crush it and throw it into your steel furnace, make stainless steel. That's how good it was. No one else had chromium that good. We used to have iron ore that good. It was called the Mesabi Range in Minnesota, and it ran out about 1948. But it was so good, we could take that iron ore. It was the best in the world. We could crush the rock and put it right into the blast furnace to make steel. We didn't have to process it or anything. We had the world's cheapest iron ore in the United States, but we used it all up. Well, Rhodesia had the best chrome, and you couldn't fake Rhodesian chrome. There was nowhere else in the world that had anything of that quality, but we weren't supposed to be exporting it, or we weren't supposed to be importing it. We couldn't keep them from exporting it. And it turns out they still sold it on the black market. And the people who were using it knew it was Rhodesian chrome, but it got laundered through some other country. And so, everybody at the customs agency kind of looked the other way, even though we kind of knew we were still supporting the civil war in Rhodesia. Okay? But officially we weren't. Anyway. So there are embargoes that work and don't work. Same thing in the oil business. I mean, the Nigerians are always cheating on the Saudi Arabians on the oil cartel. Transportation as an externality. My example here is copper tubing. I mean, you think copper tubing. I mean, copper's expensive, but it's not that expensive. It turns out all through the 1980s, 1990s, when all these metal-producing industries were going offshore to lower labor rates and whatnot, we never lost the 6 factories in the United States that made copper tubing. Reading, Pennsylvania had this old plant that I had a student do a LGO thesis down there at Reading Tube. And there were 6 of these plants in the United States. And the reason was, when you ship copper tubing, you're shipping a lot of air in the hole. Okay? Large volume. It's expensive, but it's not that expensive. Okay? You can go to the hardware store and you might have to pay $80 for a 10-foot length, but it's not that expensive. Turns out the shipping costs were too great. And so we actually kept those industries because of the transportation cost. And there's a few other industries where that's true. But anyway, that's one example. My other example here is Saugus Iron Works. Anybody know Saugus Iron Works? Anyone been to Saugus Iron Works? Saugus, Massachusetts, just up the North Shore here. Saugus Iron Works was actually another transportation story, but one where it was actually an energy crisis in the early 17th century. Saugus Iron Works was like 1619 or something. But anyway, in the 16th and 17th century in England, they were having an energy crisis. And what was the source of energy in England in the 16th and 17th century? It was wood. And wood, they were deforesting England. They had three uses, and we'll talk about this later, but they had three uses of trees. One was to make cast iron for military purposes, to make cannons for your ships. Another was also for shipbuilding. You needed the great big masts for the sailing ships. And another, it turns out, they were starting to make window glass. I told you the story about bullseye glass, and we'll talk about that some more. But they had to use charcoal to make the iron and to make the glass. And then you needed the great big trees to make the masts for the big sailing ships, man of wars and stuff. Anyway, turns out England was being deforested. And they were having an energy crisis, and they were passing laws, and I'll read you some of the historical story behind all that. But they essentially built an ironworks. When they learned about the New World, they sent people over here. They built a glassworks down in Jamestown. Anybody been to the Jamestown, Virginia, to see the glassworks down there? But they came over and they built a glassworks in Jamestown, Virginia. Why? Because they needed trees. And if there was anything they had on the east coast of North America at that time, we had trees, okay? And up here, they built an ironworks, Saugus Ironworks. It's a National Historic Site now, and we'll talk about that some later. But it wasn't this was a case where it was worth it because you had such high energy costs in England to come over here to get your energy, which was trees, okay? So the energy crisis of 1973 was not the first energy crisis. So I now have an assignment for all of you on externalities. Does anyone know have their own externality story? Where something didn't get done? You can think about it, and if you can think of an externality story, I'd love to collect them. Here's one from Caroline Joseph, who's, I think she's a second-year graduate student now. But when she did her internship project as an undergraduate, she went down to one of the oil companies in Houston, and she took this course, and I said, same thing. Anyone have an externality story? For her internship, she was supposed to be looking at corrosion tests of clad pipe they wanted to do a project, an oil project in some country. She didn't tell me the country. I don't care about the country for this purpose. And she was supposed to be looking at the corrosive nature of this oil or gas field and try to determine should they use, it's a material selection problem, should they use regular old carbon or alloy steel, which would corrode in this environment, or should they use more expensive clad pipe? That was the question that was being posed to her as part of her internship. Well, it turns out what she found out is eventually the project got canned, but it really didn't get canned. She did determine that they really should use clad pipe. It was a very corrosive product they're getting out of the ground in that country. But there were several other problems. The operating company had strict requirements to make sure a certain percentage of the construction materials were made in that country. Lots of countries have that in big projects. If Boeing sells an airplane to Korea, Korea is going to demand that a certain fraction of that aircraft is built in Korea, called offsets. So big contracts, the other country is going to require offsets. You're going to have to do some of your manufacturing in that country, so they're not paying the full freight. And another is that the country required employment of local workers. Well, that's true in Canada, okay? Right next to us here. I had the opportunity to go do some studies at a lab in western Pennsylvania that does lightning tests. And I actually had scheduled a time. And when I got there, there were nothing but technicians. And that's because they were going to be the engineers and some technicians were supposed to go to Canada to do some tests for Bombardier on the aircraft up there. And when they got to the Canadian border, the Canadians looked at it and said, oh, well, we'll let these engineers in because they have specialized skills to do these tests over the next 3 weeks in Canada, but we're not going to let your technicians in. We have technicians in Canada who can do all the technical work. So it turns out they had to send all their engineers to Canada to do technician work because it turns out just because they had technicians in Canada That didn't mean the technicians could do what these guys needed to do. Anyway, but I got to go, and I got nothing but technicians in Pittsfield, Massachusetts, which turned out to be good because they told me all kinds of stories, which is another story. Okay. Local workers, unless they've been there for more than 15 years in that country, well, those people tend to be managers. Anyway, so it turns out it just wasn't going to work for external reasons. Okay, so they canned the project. Okay. There's an article that will be posted on Stellar. By the way, I'm told that all the videos are up. Maybe not all of them, but there are links on my website now to at least the first 4 days of lectures, and we'll get the others up soon, now that we've gotten permission from my former postdoc. Okay, he's the one who runs the website. So here's an article by Norm Augustine. Norm Augustine is a very interesting person. Princeton grad. He's on the MIT Corporation. He used to be CEO of Lockheed Martin. He was asked to be the president's science advisor. He's a big-time spokesman for engineering. And so in the early 90s, he gave a talk at University of Colorado at their engineering centennial in 1993 called Socioengineering and Augustine's Second Law Thereof. Anyway, so he basically is talking about externalities from 23 years ago and how he calls it socioengineering, but he gives you a little history of what were the constraints on engineering over the last couple of centuries. And he says that we've now entered the age of socioengineering, which is my point, that increasingly, it's actually not my point, it's his point from 23 years ago, increasingly externalities influence material selection more than the actual properties and cost of the material. Okay, any questions? I'm done with externalities. Anyone think of an externality that you know about? Anyway, so now let's go into, we talked about, well, as I used to say, availability and cost were the primary drivers. But I did talk about Mike Ashby, and he has this plot in his books that gives the use of materials over the ages. And he's a structural materials person. There's a structural materials course. And so he talks about basically metals, polymers, elastomers, composites, and ceramics and glasses. So 4 classes of materials, and he has a very nonlinear scale here, starting out in 10,000 BC and moving up to 5,000 BC. And so it's nice and linear there every 5,000 years, then it jumps to every century, and then it kind of jumps to every 10 years. Sort of an interesting scale, but gives him the shape of the plot that he wants, I guess. Anyway, but he pointed out early on, we had lots of woods and skins and things that you could consider polymers or elastomers. We didn't really reduce much metal 10,000 years ago. We did some, but not much. Mostly we used stone and ceramics and glasses. And the composites were straw-making brick and paper and things like that. That was 10,000 years before the Christian era. And now we've got, he was predicting when he actually, this is actually the original plot that he had. And he's predicting essentially how, well, he wasn't predicting, he was showing how increasing use of metals all the way up to around 1960 or so. But then he was showing a decreasing amount of metals and increasing plastics and great growth of composites from almost nothing to taking over a huge amount of society. And he was also predicting in 1960 and 1980, I told you about ceramics fever in Japan and things, and how people were going to make everything out of ceramics because they don't corrode and they have tremendous strength. Well, they do corrode, and they have lousy fracture energy, or they're brittle. So that's sort of the overselling I was talking about, okay? But people were spending billions of dollars in research in the mid-'80s, and frankly, Ashby was buying this crap, okay? And it was crap, okay? Did I tell you about myself in the kitchen sink at the National Institute of Standards and Technology? Okay. So when I got back from Japan, like 1986, I was an up-and-coming material scientist at MIT. I hadn't gotten full professor yet, but I was getting to be known. And I gave a talk on what I'd learned in Japan for spending a year there studying what was going on in material science in Japan. And a great big auditorium at the National Institute of Standards and Technology in Gaithersburg, Maryland. And I was telling them about the ceramics fever in Japan and how they had 2 million people come to this scientific show about fine ceramics, how they were going to take over engines and everything else. And this is probably the premier material science laboratory for the U.S. government. In fact, I used to be on their board or their advisory committee, and I called NIST the crown jewel in the federal laboratory, or the crown jewel in the federal laboratory crown of laboratories. 700 federal laboratories, but they've had several Nobel Prize winners at NIST. Okay, just an outstanding laboratory. And I got up and said, well, the problem with ceramics is they're brittle. Now, I knew that. Everybody, Griffith knew that. He was the father of fracture mechanics. He was studying fracture of glass in 1925. He knew that. But the ceramists had sort of glossed that over because they wanted to get research contracts by saying, oh, ceramics don't corrode. And they'll, and I said, ceramics do corrode. They do develop flaws. And the critical flaw size is so small because they're so brittle that you can't even inspect for it. And so, in fact, this is not going to work. And in fact, the only high-volume ceramic materials that we use are Portland cement and toilet bowls. And I'd throw in the kitchen sink, but you have to line it with gray cast iron to give it fracture resistance. Okay? That was my hyperbole way of saying, you're all lying to me about fine ceramics. Now, Portland cement, we're going to see, we use 50% more Portland cement by ton than we do steel in the world. It is, in terms of a man-made structural material, it is number one. Okay? And it's a ceramic, even though it's brittle. And it's been around for thousands of years. And I said I said Portland cement and toilet bowls. Why did I say toilet bowls? Because if you're a ceramist, you'll find that the whitewares industry has been one of the primary industries. Whitewares is toilet bowls and sinks and bathroom fixtures and things like that. They call it whitewares, and they make them in huge quantities, as far as that goes. And I said I'd throw in the kitchen sink, except the kitchen sink has to be lined with the most brittle metal we have, just about, cast iron, in order to give it fracture resistance. If you drop something in the kitchen sink, you don't want it to shatter. Okay, you tend not to have heavy things in the bathroom sink. So anyway, Ashby was buying into all this hoopla in the 1980s about fine ceramics taking over. See how ceramics were going to grow like that? Bull, here we are in 2015 and ceramics are still, right? In fact, they've probably gone, well, it's still Portland cement and toilet bowls. Okay, composites, we're going to take over the world. What's the problem with composites? They're too pricey. I passed around that little piece of the X-33 space plane. $12,000 a pound. Fantastic if you're going into space at $20,000 a pound cost savings, but you can't afford to even make a Boeing aircraft out of composites very well, which we're learning through the 787. Plastics were just going to grow like mad. I'm going to show you how big this is, and Ashby was off by quite a bit. Okay, and metals were just going to, the metals industry was dying. Okay, well, so I listened to this for years, and I got people very upset with me because of my negative way of saying things. But anyway, I finally took some of the ideas and I wrote an article. Not that anyone wanted to publish it. I had to publish it in the welding journal because no one else cared about metals at that time. This was like 1992, wasn't it? June 1991. Article I called The Future of Metals. And I pointed out that among all the metals in the world, 95% of all metal made in the world is steel, and less than 2% is aluminum, just over 1% is copper. Steel is the dominant metal, and we'll talk about why that is. And I told you, you're going to hear me keep on talking about steel as a structural material. Well, this is one of the reasons. It's not me. I'm not the one who bought, 1 billion tons of steel every year. This is what the world buys, okay? But in here, I also talked about some of the other properties and the growth in these industries. And so fine ceramics, this is the time when fine ceramics was going to take over the world. And I pointed out, and I gave this talk a number of times, that fine ceramics had a market value in 1990 of about $5 billion annual, and the estimated annual growth was going to be 20%. Composites was about a $15 billion industry for fancy composites, not Portland cement, but advanced engineering ceramic composites. So it was 3 times as large, and it had a growth rate of 10%. Semiconductors, silicon, in 1990. We had computers back then, right? This was right before cell phones. That was only a $100 billion industry, and it had a 5% growth rate. And steel at that time was a $500 billion industry with a 2% annual growth rate, and everybody says, oh, it's got a lousy growth rate, it's over the hill, it's going to die. And you saw that in the Ashby plot, right? Metals were decreasing. Well, it turns out, if you multiply these two columns together, you find that the 2% annual growth rate on a $500 billion business is more than the growth of all these other businesses combined. Okay? Now, the problem was the steel industry was losing its shirt back then. Okay? And there was a guy named Mittal in India. Anybody ever heard of Mittal, M-I-T-T-A-L? Well, he knew that steel was an important material, and he went around buying up these old steel plants. There were plenty of steel plants for sale, and the reason was, with the Arab oil embargo and stuff, in the 1980s, the American steel industry, or the United States, had used 100 million tons of steel a year. I got these plots, I could show them to you. It's in here somewhere, I think, in this article. They used 100 million tons a year, essentially constant. But at the same time, the employment went from 500,000 steelworkers to 250,000 steelworkers in 10 years. And you'd read in the Wall Street Journal, the steel industry was dying. They were laying off half their workers over 10 years. Well, wait a second. They had constant consumption. The employment to produce it went down by a factor of 2. What happened to productivity? It went up by a factor of 2. I did that one in my head. Okay? If half the people produced the same amount of product in 1990 that they did in 1980, productivity doubled. What was the U.S. total productivity increase in the 1980s? It was 1% over all industries. In the steel industry, it was 6 or 7% increase in productivity. Remember yesterday I told you productivity isn't everything, but in the long run it's nearly everything? Well, the steel industry was remaking itself for various reasons, and we'll talk about some of this stuff later. But the steel industry remade itself. The only industry that had a better growth rate in productivity in the 1980s was the mining industry, and they were close to 10% annual productivity increase. But all Wall Street does, and all the politicians look at the number of jobs that are lost, and they say, oh, we lost jobs. Well, of course you lose jobs. If productivity goes up, you're going to have to find something else for those people to do. And there are lots of McDonald's and Burger Kings and Subways. And you can pay those people $9 an hour. Or if Bernie Sanders gets in, it'll be 15. He said so last night, right? Okay. So your Subway price is going to go, rather than a $5 foot long, it'll be a $7.50 foot long. Okay? But in any case, it's just simple economics. So you can read what I said 25 years ago about the future of metals, and there really was going to be a future of metals. And Mittal knew it. He had the money to invest in the steel mills, and now he's a multi-billionaire. Okay? But nobody else wanted these steel mills. They were selling them for 10 cents on the dollar. The fat cats on Wall Street were so bright, they knew steel was dying. And so they were going to dump it at 10 cents on the dollar. And Mittal said, I'll take that. So anyway, okay, enough for today of haranguing about my opinion of the intelligence of Wall Street.